Okay, in the previous video, we looked at the principle of impulse and momentum and how it is applied to a rigid body. So in this video, what we're going to do, we're going to look at an example of the application of this principle to a somewhat of a real-world problem. So what we have here, we have a 5 kilogram slender rod, which is initially at rest. And for some reason, we are shooting a bullet into it, and it initially has a velocity of 400 meters per second. And we're asked to find what is the angular velocity omega of the rod just after the bullet becomes embedded in it. Okay, so the assumption here is that we have a bullet which has a constant velocity of 400 meters per second, 30 degrees from the horizontal, and once it comes into contact, once it impacts the slender rod, which is initially at rest, it will remain embedded in it. Okay, so let's have a look at how we might solve this problem. Now, we could use kinetics potentially or something like that, but this really does seem as if it might be amenable to an impulse and momentum formulation. So what we're going to do is that we're going to consider a system as being comprised of both the bullet and the slender rod. Okay, so let me draw this out, maybe using some blue here. So we're going to say that this whole thing here within the dashed line is my system. Okay, so recall that the principle of impulse and momentum states that system momentum 1 plus the sum of the impulses is equal to the system impulses at time 2. And we are free to decide what our system is. We could have made our system as being only the slender rod or only the bullet, for example, but as we'll see, considering the system as being comprised of both the bullet and the slender rod, it simplifies our problem. Okay, so because these impulses, we need to remember these are external to the system. Okay, these are external impulses being applied on the system. So looking at our system now, we see that the only impulses that are external to the system are due to the reactions at O, potentially, and the weights of the bullet and the rod. So we have effectively eliminated from the analysis the impulse which the bullet exerts on the slender rod and vice versa. Okay? So hopefully this is clear, right? So we're looking at the external impulses on a system. So we need to consider what are the external forces being applied over a certain period of time on our system. Given that the force of the bullet on the slender rod is internal to the system, not external, it is not considered in our principle of impulse and momentum, given the system that we have defined here. Okay, so we can show this graphically as, so initially, we have we have our slender rod O, and let's draw the bullet here just before it comes into contact. Okay, so it's going to have a certain momentum, which we will call MB, VB, and we'll call this VB1. Okay, and we'll define this point A. Okay, so this is the point at which the bullet embeds itself in the rod. Okay, so this is our initial system momentum. And now let's show the impulses. Okay, so recall, our system is comprised of both the bullet and the slender rod. So I'm going to attempt to draw the bullet embedded inside the rod here. So what do we have? We're going to have reaction forces on the slender rod, which are applied for a certain period of time. And that period of time is the time elapsed between the system momentum at time 1 and the system momentum at time 2. I should replace this with momentum, not impulses. That was a small mistake here. Momentum. Okay, and again, we're free to choose what this time is. So at which time we evaluate the momentum. Okay, so we have reaction forces being applied over a delta t. And what else are we going to have? Well, we have our center of mass G over here, so we're going to have the weight. Okay, and I could call this m rod multiplied by G and multiplied by delta t. And similarly, I'm going to have the weight of the bullet, and again, that force multiplied by a time delta t will result in a certain impulse. And this will be equal to the system momentum at time 2. Now I'm going to pick my time 2 as just after the bullet is embedded in it. Okay, so time 1 is just before the bullet is embedded in the rod, time 2 is just after. So just after, what are we going to have? So again, we have our bullet embedded in here. It will have a certain momentum, which I can call MB_VB2. Okay. And this is undergoing fixed axis rotation, right? So we're going to have a linear velocity at g. So I can call this the mass of the rod multiplied by the velocity of the center of mass at time 2. So that's my linear momentum. And I will also have an angular momentum, which we will call Ig omega 2. And this is what we're trying to find. We're trying to find this omega 2. All right. So this is a graphical representation of the principle of impulse and momentum. So the initial momentum of the system is simply that of the bullet just prior to contact with the rod. And during the very short period of time before the rod displaces appreciably, we only have the impulses due to the reaction forces and the weights. And then what we do is that we look at just after the bullet embeds itself, the combined rod and bullet will have acquired a new momentum. It can therefore be seen that there are no angular impulses on the system. So we see that all the forces are acting, they're not causing any angular impulse. There is no moment being exerted about point O, for example. Okay, so what we can say here is that since there are no angular impulses, then what we say is that we have conservation of angular momentum. Right, so if we recall that our principle of impulse and momentum can be separated into 3 scalar equations. So if I were to be more precise and say that we have the system angular momentum at time 1 plus the angular impulses, and that would be equal to the system angular momentum at time 2. If there are no angular impulses, then what we can say is that the angular momentum about the axis of rotation 1 is equal to the angular momentum about the axis of rotation at time 2. So this is what we call conservation of momentum. And more precisely, conservation of angular momentum. Okay? So let's just stop here for a second. So we're looking here at the impulses over here. Now, if we're evaluating our principle of angular impulse and momentum about point O, this one over here, we see that we have a certain linear impulse due to the weights. Neither of these contributes to an angular impulse. Okay? These are not creating any moments that would result in an angular impulse. Therefore, we have what we call conservation of angular momentum. So the angular momentum at time 1 is equal to the angular momentum at time 2. And we need to be precise here. And here what we're saying is that this is the angular momentum about the axis of rotation O. Now this is a scalar equation, so I'm going to have to define a positive sign convention, which I will say that it is counterclockwise as being positive. So, what is the angular momentum at time 1? The angular momentum at time 1 is only due to the velocity of the bullet. And more precisely, it is only due to the velocity or the momentum of the bullet, or the component of the momentum of the bullet in the x direction. So what we have is the mass of the bullet multiplied by the velocity of the bullet at time 1. And we're interested in the x component, so we're going to multiply it by the cosine of 30. So this is what we would call, if we wanted to call this P, so the momentum of the bullet, P for the linear momentum of the bullet in the x direction. Okay? So this is a linear momentum in the x direction, but we're doing conservation of angular momentum. So we need to multiply this linear momentum by a moment arm. And that moment arm will be this one over here. So that will be 0.75. And that's it. We have nothing else that has a moment at time 1. Now again, we're considering that there are no angular impulses. So all we have to look at now is the angular momentum at time 2. So we look here, this is essentially a kinetic diagram. Okay? And we look at what is causing a angular momentum. So we have our mass of the bullet multiplied by the velocity of the bullet at time 2. And we're going to multiply it by its moment arm, which is 0.75, to get an angular momentum. Similarly, the rod will have a certain mass, a certain velocity, VR2. And you know what, maybe I'll call this VG2 to be consistent. So VG2. And then this will be multiplied by L over 2, which in this case is 0.5 meters. Now we're dealing with a slender rod. So if we're dealing with a slender rod, our IG term is 1 over 12 ml squared. So here, why don't I just write this as IG omega 2, and then I'm going to expand on this in the next line. Okay, so the velocity of the bullet initially is known, the mass of the bullet is known, so everything on the left-hand side is known. So I'm just going to rewrite this here, mb vb1 cosine of 30, then multiplied by the moment arm of 0.75. That'll be equal to mb. Now notice that the velocity of the bullet can be expressed in terms of omega. Right? The velocity of the bullet is going to be equal to omega multiplied by r, where in this case, r is going to be 0.75. Okay, so we have omega 2 multiplied by 0.75, and then again multiplied by 0.75. And hopefully this is clear why we're doing this. The slender rod is undergoing fixed axis rotation. For fixed axis rotation, we know that the linear velocity is equal to omega multiplied by r, where r is the distance between the axis of rotation and the point at which we are attempting to calculate the velocity. Similarly, we have the mass of the rod multiplied by Vg, and now this will be omega 2 multiplied by 0.5, and again multiplied by 0.5. So this is Vb2, and this is equal to Vg2, plus our Ig omega 2 term. So for a slender rod, we have 1 over 12 ml squared. Now, the mass, I'm just going to leave it as the mass of the rod. If we wanted to, we could add the mass of the bullet, but it is not really appreciable considering the vast difference between the mass of the rod and the mass of the bullet. So 1 over 12 ml squared, where that's just 1 squared, and then multiplied by omega 2. And so here we are. We have everything that we need. We've replaced the unknowns, which are VB2 and VG2, with their fixed axis rotation definitions. So we have omega 2, and omega 2. Everything else is known: the mass of the bullet, the initial velocity of the bullet, the mass of the rod. So we can isolate for omega 2 and solve, and we find that omega 2 is equal to 0.623 radians per second. Okay, so let's recap what we've done. Okay. We are looking at a bullet which initially has a velocity of 400 meters per second. It hits a slender rod and becomes embedded in it, and the system is undergoing fixed axis rotation. We apply the principle of impulse and momentum by defining our system as being comprised of both the bullet and the slender rod. This simplifies the problem because what we see is that we can eliminate the impulse of the bullet on the slender rod by considering this system as a whole. These impulses that I just mentioned, being that of the bullet on the slender rod, is therefore internal to the system and should not be accounted for in our principle of impulse and momentum. Now recall that we can apply the principle of impulse and momentum in 3 possible directions. Okay, so we can develop 3 scalar equations, one in x, one in y, and one in the angular direction. So if we look at the angular impulse and momentum, we would have the angular system momentum at time 1 plus the angular impulses is equal to the angular system momentum at time 2. Now, looking at our graphical representation, we see that about point O, there are no angular impulses. That is, there are no forces that are causing moments that would be applied over that small time delta t. So what this results in is a conservation of angular momentum equation, meaning that the angular momentum about point O at time 1 is equal to the angular momentum about point O at time 2. And this results in a fairly straightforward expression that allows us to solve for the final angular velocity omega 2.